Hi, I'm Siddharth. I just got my PhD at Penn State, and it's my pleasure to talk to you guys about doing optimization on statistical and topological losses, and why Julia is particularly an excellent tool for this. Okay, so I want to begin by giving you some motivation for why we started looking at this problem, and hopefully, you guys will sort of see why looking at it through the lens of topology is actually a pretty useful tool, even in an area like machine learning. Okay, so for a majority of this talk, I will sort of focus on this one use case in machine learning, although the stuff that I will be talking about is not necessarily restricted to this, right? So the problem setup is as follows. So you're given a source distribution, that's the stuff that you see in orange, and you're given a target distribution that has some interesting underlying features, geometric, topological features, right? So you can sort of think of the blue points as images of different faces or images of cats and dogs where there's some interesting underlying structure that you want to uncover. And the stuff in orange is just random noise, right? And one of the sort of hot areas in machine learning right now is trying to understand how you can transform the orange points to the blue points. So you start off with useless garbage data, and then you're ending up with something that is sort of indistinguishable from true signal, right? So these kind of models are known as generative models, and they're useful for statisticians have looked at this for a very long time, right? And one of the primary motivations for why statisticians have looked at this is maybe the blue points are hard to sample from and the orange points are easy to sample from, right? So you start off with something easy and then you push it forward to get something that is more interesting, right? It also sheds light on the conditional relationship that you have between these two sets of points, right? So you can sort of think of the blue points as your response variable in a regression model and the orange points as the input variables, right? So, and you want to sort of understand how is the response conditionally dependent on the inputs. And you will sort of see a problem of similar flavor if you've looked at any sort of generative models like GANs, denoising diffusions, etc. If you are familiar with style transfer, where you're sort of doing an artistic style transfer, all of these problems sort of intrinsically lie on this principle, right? So this is the problem that we'll be looking at. Okay, so what am I going to talk to you about today, right? So this package effectively has 3 different functions that are where we use Julia's excellent multiple dispatch to, expand into a collection of useful tools that you could possibly use. So the first thing on the left-hand side is an abstract discrepancy, right? So it's just an abstract structure that specifies how you're going to compare 2 different probability distributions, right? So the points that we saw are known as discrete probability distributions, and you can sort of think of this as your favorite probability metric, like the Wasserstein distance, the KL divergence, whatever, maximum mean discrepancy, etc. Okay. Then that sort of feeds into an abstract loss function, right? So this is just saying, I have something that I want to make better. So how do I measure or evaluate a loss on these points in order to get something that's better? And the last thing is an abstract backprop object, right? And this is effectively what is doing all of the optimization under the hood, okay? So the optimization is happening in the last step, but in order to make sure that everything feeds into it fine, we need to make sure that the first 2 steps are compatible with an automatic differentiation engine, right? And we'll be looking at more complex and exotic examples later on. Okay, one thing that I will mention as a remark about this is that if you want to sort of get into this process somewhere in the middle, so let's say you don't really care about a discrepancy, you don't care about metrics on the space of probability measures, et cetera. I just want to define a loss function on a distribution and then optimize it. So you can enter in step 2 and then proceed to step 3 if you want. You can get rid of step 3 entirely and just use your favorite, optimization toolkit in Julia, right? So it's hopefully meant to be flexible for different modeling choices that a practitioner would want to make. Okay, so this is the TLDR for what this package is. All right, so I will sort of get into a little more of the math and the actual stuff that you could possibly use this for. Okay, so I'll sort of try to focus more on examples on what's happening, and maybe I'll finish a little bit early, so if you guys have some questions, then I'd be more than happy to answer some of these questions. Can you guys see the little snippet of code that's there on the screen, or do you want me to zoom in? Okay. All right, okay. So this is a basic workflow for how you do those 3 steps, right? So over here, we're going to start off with this object that's an abstract discrepancy, and this one is known as the maximum mean discrepancy. If you're not familiar with it, it doesn't matter. Essentially, all you need to know is that it takes in 2 different parameters, right? So one is a kernel, right? So the kernel is what is used to measure the similarity between the 2 different disjoint sets of points. And then we define a function in the middle that's actually doing all of the computation for how the maximum mean discrepancy is being computed. And then finally, we have the dist function, right? So this is what I had from the last slide. So we have the dist function over here, the d function over here, which specifies that, okay, for a struct of type maximum mean discrepancy, this is how you dispatch, all right? Okay. Cool. So we have this in place now, right? So we can go to the next 2 steps. So I am going to define this object that's an MMD struct, and then I define a loss function. So the loss function is going to look at a particular target. So that's my y, that's a fixed parameter in this loss function. And then I just dispatch this backprop method on it, and then it does all of the optimization under the hood. Okay, there's nothing like super novel over here. There are tons of other packages that basically wrap around Flux that achieve similar things. Okay, all right. So if I were to do this optimization process now to go from the stuff that's just noise into the signal, you'll see that it kind of does well, but not really, right? So you see a lot of those pink points that are just stragglers just hanging around over there that aren't really able to really get to the real target in the distribution, okay? But this is a well-studied object, maximum mean discrepancy, right? So it says if I run this for an infinitely long period of time, those pink points should, in principle, go to the blue points, right? But we live in a finite time world, right? And if I were to do this on a more complex problem, it would be very, very hard for us to diagnose when it's working and when it isn't, right? So if you ever, yeah.
What is happening here? It looks like some kind of confusion.
Yeah, so essentially the pink points are being sort of pushed towards the blue points, and it's trying to do its best to mimic those blue points, right? But not really, right? And one of the main reasons why this happens is I have chosen an ill-conditioned kernel for this problem, so it really doesn't work, right? But I know that for this problem, the kernel is bad, but if I were to do this in an actual application, I have no way of knowing that, right? And this is something that happens, I don't know, like quick show of hands, how many of you have like actually trained a GAN successfully? Yeah, okay. Well, I guess that's a testament to, how complicated these problems are. All right, okay, so this in theory works well, but in practice, not always, all right? So this is where we are interested in bringing in the paradigm of topological data analysis, all right? So I won't, I mean, it's almost 4:30 in the afternoon today, so I won't really bore you with the mundane details on algebraic topology. But essentially, if there's one thing you need to know about what topological data analysis is, it's a framework for extracting shape information from data, right? So in this case, we have this infinity symbol over here, and something that's fundamental to this object is the presence of those two loops, right? So I can sort of like deform the object a little bit, but I would have to do something really, really pathological to get rid of those two loops in the shape, right? So homology is this tool that essentially captures that information, right? And this is sort of what I was talking about. All right, so if I'm given a collection of points, the points intrinsically don't have any shape associated with them, right? So in order for us to make some sense for what is the shape associated with these points, we're going to have to look at balls of radius t around these points, and that now gives me a topological space that I can sort of ascribe to having a certain topology. All right, so a fundamental object in TDA is this construction that's known as a persistence diagram. And essentially what this does is, as this sort of radius of this ball grows, it keeps track of all the different topological features that are born and when they are eventually destroyed, right? So on the left, you'll see the birth of a feature. On the y-axis, you'll see the death of a feature. So if you sort of look at what's going on over here, right, you'll sort of see that at some resolution over here, I start to get a loop, right? So I have a loop over here, and it essentially keeps track of this loop that eventually dies when we get somewhere here, and that leads to this red point over here, all right? So this is effectively what topological data analysis is doing in a nutshell, but it does this for every single topological feature. Okay, so why bother with TDA, right? So the reason why it's become so popular is that it gives you a really, really effective compression and representation for the salient features that underlie a data set, right? So for example, if I gave you this object over here, which is a persistence diagram, you'll see that there are two loops, one hole, and one connected component, right? So when I look at that, I automatically know that this is coming from something that looks like a torus, right? So these are actually the points that generated that persistence diagram. It's a two-dimensional representation, but I can do this for any arbitrary, d-dimensional point clouds, right? So it sort of encodes the shape information over here. Okay, so this is why we use persistence diagrams, but the issue with persistence diagrams is that they're not really friendly with automatic differentiation engines, right? So this is the general pipeline that we're interested in. So I'm given an input point cloud, I construct a persistence diagram, and then I compute some functional on this persistence diagram, and then I want to optimize this functional. So how do we do this, right? So there are a lot of theoretical papers that say that there exists a Clark subdifferential for a persistence diagram, et cetera, et cetera. But in order to actually get your software to do it, it's a real pain, okay? But it's not impossible, right? This is sort of effectively what this package is trying to do, right? We haven't sort of invented any of this methodology to do it. It's just that Julia is a lot better at accomplishing this, right? So this is just some boilerplate code over here that I'm going to use throughout the remainder of the talk. It takes in an input point cloud that's X, a loss function L, and then some optimizer, and does the usual rigmarole of optimizing it, okay? So I'm going to call this function foo, and I'm going to deploy it in different parts of the slides, okay? So the first example that I want to show you is running an optimizer on the negative entropy of a persistence diagram, right? Okay, so what is this doing? This is, if I'm minimizing the negative entropy, that means I'm trying to maximize the distribution of the points in the persistence diagram. So this means that it's going to try to like shuffle points around so that it looks as uniform as possible, right? So if I were to run this algorithm on the point cloud, this is sort of what happens, okay? All right, so let's take it a step further. And now we're going to optimize the entropy, but we're going to sort of focus on optimizing the first order topological feature, right? So the first order topological features are cycles, right? So if I were to run the same method now, but on a different loss function that tries to optimize the persistence of the loops, right? This is sort of what it looks like, right? So it tries to use the same points to create as many loops as possible. Okay, so this is telling us that, okay, we're on the right track. All right, so what I've shown you right now are ways of optimizing point clouds, okay? But this isn't the only way in which you can compute persistence diagrams for topological data analysis, right? So it's not just points that have shape, but it's also different functions. Functions also intrinsically have some shape. So the way you describe the shape of a function using a persistence diagram is through this notion of what is known as sublevel or superlevel persistence, right? So it's effectively what you do is you're given a function, and then you start to look at like sublevel or superlevel sets. Those are the x's for which the corresponding f of x value is greater than some level t, right? And now I start to vary t, and I end up with these interesting topological spaces where different features are born, different features die, right? So this is sort of what goes on when I do this, right? And then I can compute a similar persistence diagram over here. Right? So in practice, the way this is done is that when I start to look at these level sets, I have to discretize my underlying grid, right? So I have some function that lives on a grid. So you can sort of think of this function not being transformed to look like a histogram, right? So the histograms now have these bars, right? And every time this level t touches a bar of the histogram, that cell gets activated, okay? This is a sort of intuitive way to think about the way this is done. The way this is actually implemented for computing a persistence diagram is a little more complex, right? So I'm given a function f that I want to optimize, and then I'm given this grid of some resolution r. So the function and the grid together form this thing that's known as a cube map. The cube map computes a persistence diagram, and then we have a functional on that, and then I want to backpropagate the gradients over there, right? So again, this isn't something new that we've come up with. There are actually analytical expressions for this for simple functionals, but if you sort of use the right tools in Julia, you can actually do this pretty efficiently. All right, so this is an example that I want to show you where we're going to do this by looking at an image as a function, right? So I have a 128 by 128 image. I can look at that as a function. I can then start to optimize the function that lives in the image. So it's going to transform the image. But I'm going to do that in a specific way, right? So in this example, we're going to look at unsupervised image segmentation. So effectively, what we're going to do is, for that image, we're going to compute a persistence diagram. And then we're going to say, okay, I want to minimize the entropy associated with this persistence diagram, right? So that means if I have some ephemeral topological features, I want to sort of squeeze them down because that's how I reduce entropy. Small little variations get crushed down, right? And then I do this optimization. Okay, so this is what you get, right? So this is an image of a cell, and I just run this for 20 or 50 maybe, 50 iterations, and then you start to see a little more structure in this image. I'm not using any deep learning architecture over here, no UNet, none of that stuff. It's just optimization of the entropy. Okay. So this is image segmentation. Another example that I want to sort of quickly run through is high-dimensional sparse regression. So this is known as image on scalar regression. So effectively, I'm given a matrix, I'm given a collection of matrices X, and my beta, that's my sort of coefficient underlying ground truth, is also a matrix, but it has some sparse underlying signal. So in this case, it's just a circle over here. But I'm going to look at this in a really, really really low signal to noise regime. So it's a 20 by 20 matrix. I only have 400 points. So the matrix is just invertible, right? The gram matrix, sorry. And I'm adding about, noise with variance 3 over there. Okay, so this is a particularly hard problem. So the way we can sort of do this is we can run just vanilla linear regression over here to see what we end up with. More popular techniques are based on lasso or graphical lasso, fused lasso, etc. In this example, I'm just going to run just vanilla lasso. But what we're going to do now on top of that is we're going to piggyback this extra topological loss on our loss function, and we're going to do these 3 different optimizations to see what happens. Right? So you can sort of see that the regression estimator is just not able to recover that signal over there. Lasso does a pretty decent job, but penalizing it with this topological loss function sort of simplifies the amount of noise that we have and also accentuates the real information that we're looking for, right? Okay. All right, so all of the examples that I've shown you right now, like entropy, et cetera, these are just pure functionals on a persistence diagram. Right? I haven't told you how we can go from source to the target. Right? So in order to go from the source to the target, I need to be able to compare 2 different persistence diagrams. And for this, we need to sort of look at what is known as a partial optimal transport metric, right? So if I'm given 2 different persistence diagrams, I do an optimal transport, but it's not a vanilla optimal transport. I'm allowed to go to the diagonal and not incur any cost after that. So the diagonal has like infinite mass, right? So it's known as partial optimal transport over here. Okay, so we want to be able to do propagate gradients through this computation over here, right? And this can actually be effectively done by looking at the fixed point of the SYNCHRON algorithm for this. Right? So this is the first thing that you see over there. We look at an entropy regularized version of this partial optimal transport problem. And then we also have another method that's not like theoretically well-founded, but is really, really fast. Okay, so that's the second box that you see over there. And this is just like a quick and dirty benchmark over here. You can sort of see it's about like an order of magnitude faster to use the second one. But both of them are AD compatible. All right, okay, so the way you combine statistical and topological losses now, so this is where the backprop function comes into play, right? So I have 2 different loss functions, and I want to be able to optimize both of them simultaneously, but I can't just combine them. I can't just add them because they live on 2 different scales, right? So we need to think of like novel ways to do that optimization procedure, and the backprop function has like a bunch of different methods from literature for how you can sort of do that. So I'm just going to pick one of these methods over here. So this is known as alternating backprop. If you're familiar with like splitting techniques, this is effectively just doing a splitting technique over here. It optimizes one, then it optimizes the other, back and forth, okay? All right, so this is the example that we looked at in the beginning of the talk, right? And this is what happens when I just add a little bit of topological regularization over there. All right, okay, so I am running low on time, but I'm also just almost done. And I just want to close with like a couple of really, really quick remarks over here. This is still like in like pre-alpha stages, okay? Version 0.0.0.1. All right. Lots of fun things we can do with this, right? I'm sort of particularly fond of the distances.jl package. I don't know how many of you use it regularly, but I think it's a really, really well done package. And this was sort of like was one of the primary inspiration that I had for making this, where you just have like 2 or 3 different functions, and then you use multiple dispatch to depth, okay? But it would be nice to sort of interface this with other packages. In particular, I want to sort of shout out to Eric Hansen, who wrote this excellent package called Unbalanced Optimal Transport. Oh, is that you? Okay. Okay. Oh, I didn't recognize you with the mask. Okay. Well, so over there, unbalanced optimal transport, you want to sort of optimize the weights and you want to optimize the support, right? And this is a sort of similar thing that we saw, like on the cubicle grid, we're sort of optimizing the weights. On the point cloud, we're optimizing the positions of the support of these measures. So it would be nice to like bring in that abstract measure and then propagate gradients into the measure in some way. And of course, implicit differentiation.jl sounds super exciting, but has issues dealing with non-vector data types. Okay, so I want to also shout out to Matteo Chufar. I've never met him, but all of this is made possible by the excellent ripsitter.jl package that he's written. It's absolutely, I mean, it's a work of art. You should have a look at that repository just to see the amount of work that it takes. And also Yusuf, Karthi, and Kush at IBM Research, where we started working on this together last year. All right, excellent. So here are some references, and these are the QR codes. You can check out the slides and also check out the package. Pull up, file an issue if you just want to like discuss something, whatever. I'd be more than happy. All right, thank you.
Thank you. Great presentation. I think we have time for maybe one question, if anyone wants to ask. Yeah, just ask, you can just say it. All right.
So is there like one thing where AD might be extremely useful, or is there some, so to say, killer application of AD which has not been done before in this use case, so to say, with this persistent homology?
I'm sorry. So your question was, what is one killer application of AD for just persistent homology? Yeah, I mean, like all of the stuff that I showed you were just like toy examples where you just like play around with it. But I think it would be super interesting to like actually apply it to, you know, real world data sets, right? These are very novel applications that people haven't really looked at. So, you know, feel free to check out the package. If you want to, you know, just discuss something or you have some idea, feel free to get in touch with me as well.